Okay, this is my video report on Lab 3, Charges in a Conductor and Gauss's Law. The main goal of this lab was to investigate Gauss's Law by simulating the behavior of charges in conducting surfaces. We also observed the arrangement of charges at equilibrium, so in the simulation we had the charges go to equilibrium. And then we observed how they looked once they reached equilibrium. And we also computed and compared net electric field values for the different surfaces because we used two different main surfaces for this simulation. We started using a program within Python to visualize charges on two different surfaces. The surfaces were a sphere and a cube. The program allowed us to change the number of specific charges that we wanted to observe. And once we ran the simulation, all the charges would scatter to the surface of the two objects, the sphere and the cube. And once they reached equilibrium is when we would observe them. And here in a minute, I'll show you two examples of what I mean by that. After we were done viewing how they interacted with different charge numbers, we then used a different program within Python to compute net electric field values at different points away from the origin that the cube and the sphere were centered on. Something similar was done for a point charge, but that was not done using the simulation, and I'll come back to that in a minute. These are the two examples I mentioned a second ago. On the left here, we have a sphere, and I believe for both of these, we used 200 charges. So we have a sphere on the left, cube on the right, and what I meant by rushing to the surface is at the beginning of the simulation, all the charges started in the center at the origin, and then quickly shot to the surface and moved around until they all kind of fell into a spot that had the most equal distances away from each other as possible. And once they all kind of stopped moving, that's what we call equilibrium. So for the sphere, you can see they're all kind of, I wouldn't say uniformly spread around, but they are pretty well spread apart from each other. On the cube, there's a slight difference where you can see on the edges and specifically in the corners there is a higher concentration of charges, and some of the charges couldn't fit in the corners or on the edges, so they then spread themselves out across the different faces of the cube. This is a table showing the values of the net electric field at the different distances away. Here you can see the point charge, the conducting sphere, and the conducting cube with 5 different values for each. One at 0.5 meters away from the origin, 0.15 meters, 0.1 meters, 0.05 meters, and 0.01 meters. All of them away from the origin. For the point charge was on the origin basically because it is a single point. The conducting sphere was centered on the origin with a radius of 0.1 meters, and the conducting cube was also centered on the origin, and each of its side lengths were also 0.1 meters. And here we have a plot with the values that I showed on the table. There is each of the different lines represent the point charge, the sphere, and the cube. The blue line with the X points are the point charge, the squares on the green line are the cube, and the circles on the orange line is the sphere's values. The lines have no actual mathematical meaning, they're just there to help you see where the points go. So as you can see, when you look over at 0.5 meters away from the origin, all of the points start at the same, all of the values came out to be the exact same. When we moved down to 0.15 meters away from the origin, The point charge and the sphere were basically dead on with each other, and the cube was slightly off, but still fairly close, so I'd say they're all within the range of each other. When we move to 0.1 meters, however, things change slightly with the sphere, because the sphere has a radius of 0.1 meters, and if you're measuring 0.1 meters away from the origin, that means your measuring point is actually on the surface of the sphere, which makes your measured values very unreliable. So we're just gonna, on the table, I marked them as NA, non-applicable, but here I just marked them as 0 for sake of the graph. For the cube at 0.1 meters away from the origin, you can see since we're closer to the face of the cube, the charge went higher, the net charge went higher, and with the point charge, it is actually even higher than that. When we move on to 0.05 meters away from the origin, this is when the measured point is actually on the surface of the cube. That's why it drops way back down to 0 again, which on the table I have it marked as non-applicable, but for the sake of the graph I just have it as said 0. The measure for the sphere is 0 because the point of measurement is within the sphere, and since the point of measurement basically measures how much charge can be measured at that point, and since the point is inside the sphere and the charge of the sphere radiates outwards, there is no charge being picked up at that point, so that is 0. I'll come back to the point charge in a second. For the measure of 0.01 meters away from the origin, for both the sphere and the cube, the measured point is within the surfaces of the shapes, so both of the measures are 0. Now moving back to the point charge, when you're looking at 0.05 meters, I did not actually have them on the graph or the plot, on the plot. They are not on the plot. That is due to the fact that they shoot way up really fast. So for 0.05 meters, the measurement's actually close to 20. I think it's like 17.8 or something like that. It's on the table. And for the measure at 0.1 meters, I'm sorry, not 0.01 meters, it shoots way up to almost 450 microcoulombs. And that's because it's getting really, really close to the point charge, but not quite touching the point charge. So the charge is going to be really, really high. Now, ultimately, we accomplished the original goal of computing the electric fields at different distances away from the charged surfaces using the help of Python. Using those values that we computed, we then made tables and plots that could show the comparisons between the point charge, the conducting sphere, and the conducting cube. And the plot allowed us to see the differences in how the charges acted once you got closer and closer to the actual charges themselves. So yeah, that's about it.